Yeah, hi everyone. So today I want to talk about scaling PyTorch model training with minimal code changes. So I want to show you a few tips and tricks how we can make our PyTorch models train much faster without having to put too much effort into changing the code. So we will take an example here, a vision transformer that I trained from scratch. And this vision transformer took about 60 minutes, that's approximately an hour, with a test set accuracy of 62% as a baseline here. So the details are, I would say, not that important. So that's a very basic vision transformer that I trained on a very simple data set. To keep it short, we won't dive too much into the details of this vision transformer. But if you are interested, the code is here on my GitHub repository here, if you want to check it out. And all the examples I'm showing you in the next couple of slides, they are also in this GitHub repository. So if you are curious about more details, you're welcome to check out this repository. And if you have any questions, please feel free to ask a question in the discussion section or here in the comments, and I will be happy to chat. So one of the main points I wanted to get at here also is that it's 2023 and training from scratch often does not make sense anymore. So with that, I mean, usually when we train models, modern deep learning models, we usually start with a pre-trained model. So for example, when we work with large language models or vision transformers, we usually use a pre-trained model and fine-tune that pre-trained model. So when I do that, when I use a pre-trained vision transformer here on the right-hand side, and I fine-tune it for 3 epochs, I can achieve 95% accuracy in just about 20 minutes, which is a big improvement from the left-hand side, where I try to train this vision transformer on the same dataset from scratch. Now, so here's just a summary because the code view was a little bit small. Just in bigger pictures, we can achieve a way better test accuracy using a pre-trained transformer that we fine-tune. And of course, it often also requires less epochs, so it usually takes much less time than training a model from scratch. So one way of doing that is using Fabric, which is a fast and lightweight wrapper library or API around PyTorch, which allows us to, let's say, use advanced features in PyTorch very conveniently. So Fabric essentially is a way to bring these advanced functionalities without having to restructure our PyTorch code. Here's an asterisk because there is one catch when we are using Fabric, and that is 100% free and an open source library. So if you want to use that, you have to install the Lightning library, an open source library, and then from there you can import Fabric. If you're familiar with PyTorch Lightning, so it's essentially by the same creators of PyTorch Lightning, except it's a bit, I would say, leaner. So that means Fabric is essentially a simpler or more lightweight way of bringing this advanced functionality of PyTorch Lightning to PyTorch models. So I will show you, first of all, before we see the speed advantages, I wanted to show you first the small modifications we have to make. So suppose we have the simple PyTorch code here shown on the right-hand side. So I kept it very simple and very abstract, only focusing on the main parts. So what we see here is that we are importing a data set. We are defining a PyTorch model, for example, our vision transformer. We have a custom PyTorch data set. And then when we have a forward pass, what we usually have is a loss function. Then we initialize the PyTorch model, initialize our optimizer, initialize the data loaders, and then we usually call the model on the inputs, compute the loss, backpropagate using .backward, and doing a step with the optimizer. So if you have coded in PyTorch before, this is something you have done probably 1,000 times. So there's nothing really fancy or new in this code here. So the main part I wanted to focus on is the little changes that we have to make when we want to use Fabric, which then in turn allows us to use a few more of these advanced features in PyTorch more conveniently without having to restructure any of this. So here highlighted are the small little changes that I was just referring to. So on the left-hand side is the code, the PyTorch code that I just showed you. On the right-hand side are these little modifications if we want to use Fabric. And you can see it's only 1, 2, 3, 4, 5, 6 little modifications here. So the first one is importing Fabric. The second one is here instantiating a Fabric object. Then using fabric.setup on the model and the optimizer. and then also calling fabric.setOutDataLoaders on the data loaders. And then, yeah, essentially in the forward pass, the only little difference here is that we call fabric.backward on the loss instead of calling loss.backward. But yeah, these are the only little small changes that we have to make here if we want to use Fabric. But yeah, since this was a bit fast and there was a lot of information on this one slide, let me do this again step by step, one at a time, so that you can really see one change at a time before you see the whole big picture and before we apply it to our vision transformer. So the first step, like I mentioned, is importing Fabric and then instantiating this Fabric object. So when we instantiate a Fabric object, there are a lot of options. Here I'm showing you a few simple options using a CUDA, so a GPU accelerator, optionally using multiple GPUs if we have them, and then defining a multi-GPU training strategy. But we will get to that more in detail later. So the second step here then is setting up the model, the optimizer and the data loader. So here only 2 lines of code to set up the optimizer, the model, and the data loader. Then the third step here is calling fabric.backward on the loss instead of the usual loss.backward. So if we do now a performance benchmark here with plain PyTorch and Fabric, we see that we get exactly the same performance. If you see a little a fluctuation, that is due to randomness, but that's what we expect because Fabric is just a wrapper around PyTorch, so there's nothing really I would say fancy happening yet. So that's just like the same PyTorch code, just using Fabric now. So as a baseline, we can see we don't get any faster or we don't get any slower. The magic happens when we, for example, use advanced techniques like mixed precision training. So we can see here with mixed precision training, we cut down the training time from about 18 minutes to 6 minutes while maintaining the same predictive performance here on the right-hand side. And yeah, this is great. And so how do we achieve that? When we use Fabric, it's really just one line of code that we have to change, or not even a whole line of code, just maybe 30% or half of a line of code by just adding this argument here, precision BF16 mixed. So BF16 mixed here stands for brain float 16 and then mixed precision training. So what does that mean? So usually when we train models on a GPU, we use 32-bit precision, which is shown here at the top. So it's essentially just a visualization of how much precision we have, like the fraction here, how many numbers behind the decimal point are, let's say, accurate. And then when we use half precision or float 16 precision, you can see here at the bottom there is less precision, so the representation is less accurate for the numbers after the decimal point. Now, brain float 16 is I would say, special version of float 16. Not all GPUs support that, but if your GPU supports that, I would usually recommend that one. It usually can represent larger numbers. It has even a bit less precision, but you can have a larger dynamic range, actually exactly the same dynamic range that float 32 has. And when I was training large language models, I noticed that usually bfloat 16 works better than float 16, which means it's a bit more stable. So sometimes when you use float 16, especially if you use pure float 16 training, you may get nans in the loss, and bfloat 16 is usually a bit more robust. But to be honest, both work fine. So feel free to choose either or, especially if you're using mixed precision, not pure precision. So mixed precision is essentially a trick that uses both 16 and 32-bit precision so that there is no loss in accuracy. So how it works is essentially it takes the 32-bit weights, converts it to 16-bit weights, then computes the gradients in the 16-bit representation to save GPU memory, and then convert it back to 32-bit gradients, then use the 32-bit gradients to update the parameters, and then continuing on. So in this way, we usually can cut down the training time by a lot because computing the gradients in 16-bit representations is much faster than 32-bit, and also it saves often a lot of memory. So if you are memory constrained or compute constrained, mixed precision training is actually a great way to accelerate the training without having to, let's say, take impacts on the prediction accuracy. Now, another technique is, of course, multi-GPU training, but only, of course, if you have multiple GPUs. But if you have multiple GPUs, it's great, to take advantage of that, to train the models even faster. So one of the more advanced techniques behind multi-GPU training is fully sharded data parallelism. So there are actually a lot of different methods for multi-GPU training, or multiple different paradigms. There's model parallelism, data parallelism, pipeline, tensor, and sequence parallelism. And I would say model parallelism and data parallelism are the classic variants. Pipeline is a bit, I would say, more novel. Sequence parallelism is something we use for LLMs sometimes. But tensor parallelism, I think, is one of the really cool things, because it enables us to train models that usually don't fit into a single GPU anymore, because it's essentially dividing the tensor. So fully sharded data parallel training uses essentially both data parallelism and tensor parallelism. So in data parallelism, what we do is we usually divide the mini batch and then have a copy of the model on each of the GPUs. So here I'm showing two GPUs where each of the GPUs gets, let's say, a subset of the mini batch. So usually we refer to them as micro batches. And this helps essentially to train the model faster, because we can iterate through the data set faster by having multiple GPUs work in parallel. And it will, depending on the method, it will then average the gradients or average the loss to get to the data set or get through the data set faster. So tensor parallelism is a bit different. It divides the model across GPUs. So if I go back, data parallelism divides the mini batch across devices, but it doesn't save you memory, because one GPU has to fit still the whole model here. Whereas tensor parallelism splits the model, so that if we have a large, let's say, large language model or a large vision transformer, we can have it on multiple devices. We can break it up, and that allows us to train models that we usually can't train. So why or how does it work? So if you think back of how matrix multiplication works, there are essentially two ways we can distribute that. We can distribute it by row or by column. Here I'm showing just by column for brevity. So for example, if you have this matrix multiplication here shown on the left-hand side, what we can do is we can break that up into two operations. So you can think of this operation here at the top and at the bottom as two separate computations, and we can carry out each of the computations on a different GPU. And then we can concatenate the results back to get the original results. And so in this way, we can distribute this large computation, if these are two large tensors, across multiple devices. And how we can enable that in our PyTorch code is again by adding just a small little change here to our fabric initialization. So here, let's say we have 4 GPUs, we set devices to 4, and we select the strategy fsdp, which stands for fully sharded data parallelism. And of course, it's just one of the million strategies. You are also free to experiment with other ones. For example, there is deep speed and many other techniques, or colossal AI. There are many advanced multi-GPU paradigms. I like fully sharded data parallel because it's already part of PyTorch, so you don't need any additional libraries for that. But this is just one of the techniques. And if I then use fully sharded data parallelism and train my model on 4 GPUs, I'm cutting down here the time that it takes to only 2 minutes. So I'm going from the original model, which trained in 18 minutes, down to 6 minutes when I use mixed precision training, and then down to 2 minutes when I use fully sharded data parallelism with mixed precision training. So this was a very short talk to just show you some of the advanced, I would say, data or training acceleration ways we have available in PyTorch, which are usually really tricky to use. So if you ever coded distributed training in PyTorch, it requires quite a few code changes. So with Fabric, we can make this a bit easier. And of course, it's an open source, a free library, so there is no downside of using that. So if you have any questions, as you know, you can find me on social media, or you can also check out my website where I have more information about certain things. And yeah, the code, like I mentioned, the code in the slides are here on GitHub if you want to check them out. And yeah, what I've been up to lately is I've been really focused also on writing a lot of articles. So you can also check out my Ahead of AI newsletter, or rather magazine, where I post about things related to large language model training, a lot of technical stuff, recent research highlights and explanations and so forth. So yeah, if you want to check that out, I would appreciate it. And with that, yeah, I hope you liked that video. And if you have any questions, please feel free to ask anything in the comments or in the discussions on GitHub. So yeah, see you then.